record.
Well, hello everyone. So this is, I think, session 10, maybe? We're discussing chapter 10. I don't know if it's session 10.
Session
Session 9.
But chapter 10.
Oh yeah, because chapter 6 is basically a one-pager. So, this week is the onion routing chapter we'll be discussing. And I don't know if you guys have noticed, but it's I find it's pretty cool because they're developing the book as we're getting through it. I don't know if you've noticed, but like these chapters didn't exist like 3 weeks ago, and they're just pushing them out right now. So pretty cool.
We gave them a little bit of incentive.
Yeah. So yeah, that's it. Let's get going. I think that chapter 10, onion routing, if the general idea, if you were familiar with the idea before, not like from a software technical perspective, but more like Wikipedia entry level page. The first almost like third of the chapter is pretty good. It sort of like solidifies maybe what you understood, or what I understood anyway for me. I don't know if anybody else has anything to say about the first third, but
I like their envelope graphics a lot. That was very useful, and I feel validated because I think on an earlier call I kept talking about like a briefcase or like cramming briefcases into each other. So I was glad to see the metaphor of sticking objects inside of other objects was a good metaphor.
Same, yeah. It blew. This was a few months back, but I was watching the MIT cryptocurrency course. I think it's called cryptocurrency design or something, and the idea of like wrapping. They're doing it with hashes, but you can basically wrap a commitment for a secret and hash it, and then have that hash be itself padded and hashed, and then itself that can be hashed and padded, and so you can go into any number of secrets that you can really reveal sequentially, and they each just contain the hash of the next one. So it's this is, I think, makes it powerful and easy to grasp.
So you just brought up the topic there of filling, right? Of that was kind of one from later in the chapter where they get into kind of filling out the onion, and that was one question I had. If now is a good time for it, was I was reading about this concept of how when they're passing, one node is passing the onion to the next node and so on, they essentially, once they've stripped out their information, that they've gotten to the envelope inside of the envelope, they then have to add extra data onto the end of the onion so that the next node, every node that receives the onion, feels like they're the first of 20 hops. They never, even if they're the 19th hop, they still think that they're the first of 20 hops because of that excess data, that filler data that's been added. And I was curious about like what incentive a node has to add that filler data. Like what would stop a node from just not adding the filler data? And like say it was sloppily designed software, what would stop the node from just not adding that filler data and then passing it on?
That's a good question. Or
I think the protocol will fail. It's enforced in the protocol, I think. So, but there is a certain fixed byte length of onion data. So if the node fails to like attach his data after like stripping, attach the random data after stripping his own, then the size of the onion will change, and the other node will say like, nah, that's not a good onion, so they will not take it. I think that's gonna happen.
That makes sense.
because they have like fixed the size to 1.3 megabytes, right? So it's always that many bytes of data for each onion, so it cannot be bigger than that, it cannot be lesser than that also. So that way kind of it's like enforced by the protocol itself.
Wait, so an onion is always 1.3 megabytes?
Yes, it's always 20 hops worth of data.
That seems like well, I understand the need for 20 hops. I'm just trying to think scalability here. If essentially, with the way I understand Lightning payments to work, that they're atomic and all this, you essentially could try to route a payment and it could fail. And it just seems like with the amount of payments being routed through the Lightning network, I thought my understanding from previous chapters was that there's not really a way to ensure that you know that a payment is going to work. So you're just trying to route a payment and seeing if it succeeds or fails. And you're just, in order to get the payment from point A to point Z, you're just basically attempting to route the payment multiple times until one of them succeeds. And I guess if my understanding of that is correct, then it seems like that adds a lot of overhead to the network if every single payment attempt is 1.3 megabytes in between every node.
That's true actually, and that does create a lot of overhead, and these routing guys are like trying hard to solve that problem, like so that they don't have to like do this trial and error method, and like they can have like better intelligent way of handling this. But yeah, like it's a trade-off. I think I remember like listening to a presentation regarding this topic. Like it's a trade-off between like privacy and scalability, and we kind of see this trade-off pop up many places in Bitcoin and Lightning and like blockchain in general. So this is one such trade-off where like in order to improve privacy we kind of like have to like intentionally create like larger data than we need to.
Makes sense.
It seems like it's also interesting that you're actually using more bandwidth, network bandwidth, if you have more hops in your path, and that's controlled by the source because they have source routing. So if I really wanted to use a lot of Lightning network bandwidth, I'd make a 20 hop and I'd touch as many nodes as I could. Of course, I guess that has a lower chance of succeeding because one of those hops might not accept the channel. But yeah, I thought the whole source routing thing was interesting too, just because it really, the only person who knows the route being taken is the source of it, Alice in this case, and she kind of determines how many times. But I guess back to the bandwidth question, even though the packets themselves are fairly large or the onions are pretty big, they really only are being transmitted hop to hop. Because I saw something recently on Twitter that said most of the network bandwidth is actually the gossiping. That's actually what uses up the most Lightning bandwidth because it has to go to everybody. So from a bandwidth point of view, that might actually be the bigger problem. They can somehow get gossiping to be more efficient because that's a broadcast, goes to everyone.
I see.
That really hurts the really hurts scalability more. So yeah, I think it's also true that
then?
What's that? Was that Thunderbird?
I was just wondering, didn't mean to cut you off, but what happens if you have a malicious node that purposely builds, routes that'll fail, at the 20th hop or whatever,
right?
And fires like 100 of those a second? Is everybody along the route gonna attempt, and then they each realize that it fails, and they need to, I feel like you could really span.
I think that's what happens.
Okay.
In fact, I've even heard of
like a DOS attack, right? Like you can like heavily DOS your peers, like your channel partners in this way, like repeatedly sending him like malicious hop like onion data, and he will try to like route it and see failings and like report you back. I'm not sure, like at some point like Bitcoin have this ban score for its peers, like if so they set a score, if somebody behaves badly and the score goes a threshold, they ban that peer. I'm not sure if Lightning does that, but it seems like reasonable to have something like that.
Yeah, for sure.
Well, what I was thinking too is because of the process of the onion routing, like if you don't know who is the source, right? You just know your one hop, then can you are you going to ban basically the peer that's sending those, but it's not really their fault, it's the one before them? I wonder how that's handled. You'd have no way of knowing if you're banning the right peer or if it's just somebody along the hop. And so that'd be another way you could DDoS, and then you'd make other people ban peers that are totally not malicious. But anyway.
Yeah, you could actually imagine.
Yeah, that does make sense.
Yeah, you could imagine a bunch of people. You could have a bunch of Sybil nodes too, all targeting one node, sending a bunch of bad channels through them or bad onions through them, just so that if their peers are counting how many failed connections or using that as a metric. I guess maybe what it boils down to is you can't really use failed onions as your metric. You have to use something else, because that, like you said, you really don't know where those are coming from or who's causing them. In fact, even peer-to-peer, because Alice could be generating them and Bob wouldn't know if they came from Alice or they came from someone beyond Alice. That's part of the, thing we talked about last chapter. So yeah, I don't know. I haven't heard of anything, but that's a really interesting question about how to prevent griefing, basically. Yeah.
All right.
More I'm thinking about it, it's interesting problem. Like all these onions are hopping around the network. How do you know which one is good onions and which one is bad onion, and what stops the network to fill up with bad onions? Good question.
Yeah, and it's not just that you're using up people's bandwidth, but you're actually potentially using up their capacity, right? Because as you set up the route, you're actually creating the HTLC set using up part of your channel capacity, I believe.
Yeah.
You're at least reserving it for those channels. So it really is a finite resource. And then there's these fixed timeouts that you have to wait for, probably for the route to succeed or fail.
But that might not create too much effect, because the failure is, I think, doesn't take much time. Like if you the nodes figure out the onion fails very soon, right? So they, whatever the onion, they will quickly hop into how far they can reach, and at the last point they will say on it doesn't go up further, the entire thing will fail. So it will fail pretty quickly. So it will not be suitable to create this kind of liquidity problem. But it can take lot of time if it's directed toward a single channel partner or single peer. It can take up lot of its resource and computation power to create all these update and delete HTLCs. So that takes to and fro communication every time that happens, right? So that can be resource exhaustion attack or something like that.
Yeah, I mean, it almost makes you wonder if, this is totally off topic, but if eventually people might need to start doing sort of a bond for their nodes where they lock up a certain amount of Bitcoin just to prevent sort of Sybils, and just to, I don't know. I guess you still don't really know who the bad guy is still, so that doesn't help.
Yeah,
I don't know.
And I think they probably have a better answer than us, the Lightning folks. Otherwise, there are lots of civil protection mechanism like fidelity bonds and stuff like that they use in coin joins and those kind of protocols, right? Because of this reason only. So otherwise, they probably would have used something like that. But there is probably a good answer that we are not catching here right now, that says this is not a problem.
Yeah, I guess not, or maybe not a problem yet, and they don't need to worry about it with the size of the network as it is.
I mean, if anything, I would hope that the solution would be that, or part of the solution would be that, if somebody does want to perform an attack like this on the Lightning Network, they essentially want to drain somebody's capacity or, clog up their bandwidth with, payments are going to fail, this kind of thing. Well, they have to have Bitcoin locked in that lightning channel. So the question then becomes, is there a better thing that they could be doing with their Bitcoin? Like, if somebody,
That's a very good point. That's basically a fidelity bond then.
it's like,
That's
I mean, it's like an opportunity cost. Like you could still, like, yeah, you could do it. If I wanted to mess with you, I could open up a lightning channel with you, and or
but that doesn't scale, right? Because for
yeah,
that you need to have like real sets. That's why like
yeah,
the attack doesn't scale in that way. So it's kind of like an inherent fidelity bond inside the protocol itself, because you have to lock up bitcoins to do that. So that suddenly, because you cannot like do it once in a day, right? So properly attack someone, you have to do it like constantly and with lot of HTLCs.
yeah. If
So
you could rebalance, if you could, DOS them like a bunch of times by creating another node on the other side of the network, and like try to like constantly rebalance through their nodes or something, and you could really try to mess with somebody. But again, you have your Bitcoin locked in those channels on those two nodes. Could you do something better with your money? You're missing out
yeah.
on something.
Right, and every successful hop will gonna cost 2 sats, right? So you have to pay for the routing also.
Yeah, you have to pay those routing fees too. And, I don't know if that's the
Yeah,
solution, but that's the only thing I can think of.
I'm thinking of just that probably does make sense. The other thing that I've seen people do with these kind of situations is you just have rate limits. Like it might just be simple enough to say, you're not going to allow, more than 1,000 per second or something like that. Some reasonable number between, that you would expect from a typical node. Although I don't know. That's just another.
Well, to your
depending
point,
on the size of your node, may not be true.
I think it already done in the protocol. Like remember in the open channel messages, there is this parameter called like uh, maximum HTLCs in flight or something like that. So that's
Okay.
the limit of like amount of HTLC that a channel can handle, right? So that's kind of like rate limit itself. So more
Yes.
HTLCs than that will not be like registered as a payment in that channel.
So those two things combined probably do provide some protection, because you've got, like you guys said, the fidelity bond is your sort of channel capacity plus the rate limits. So you can only have so many per locked up channel.
Yeah,
So
and like the rate limit was somewhere like 436 or some number like that. So it's not too much HTLC. So it's not gonna
yeah,
be effective to like attack someone in this way if there is like only 430 HTLCs that you can send before like things start failing. And things
right.
starts failing very quickly, right? Because onions fails very fast.
Yeah. That must be part of the answer there, I think.
Yeah.
and on this topic of just routed payments failing, I'm curious if there's like an average number of like a common average for how frequently payments fail. So like you can imagine that depending on your channel partners and your connections, on some days, at some parts of the day, most of your payments may go through very easily, and then other times you may have a lot of failed payments. It's just going to vary depending on the channel capacities and all this. But on average, is there like a 50% of payments fail and 50% of payments succeed, or can it be distilled down to some number like that? And then if it could be distilled down to a common average, then you might be able to, from those statistics, draw some other conclusions like, okay, if I have 30 channel partners and one of them statistically fails more frequently than the other 29 channel partners, then I don't necessarily know that channel partner is malicious, but I know that either that partner or some partner that they're connected to is either malfunctioning or malicious or something to that effect. But I'm not a statistician, so take that with a grain of salt.
I think like it would be hard to do because it's a live network, because everything is changing all the time, right? So uh, it will be hard to measure also. I don't know. Go ahead,
Actually,
Steve.
I was going to say there's one exception to that rule, which is if you have with your channel partner a private channel, then I believe that everything is if I understand correctly, if it's a private channel, then people shouldn't be routing through it. So you could at least kind of get some idea that if there's bad stuff coming there, it's coming from that partner. Does that seem, well, is that true? Or is it only that they know about it, they can still route through it if they have other channels on public peers or public channels?
Yeah,
I think the private information is conveyed in the invoice itself. If the receiver knows about the private channel, then he can hint the sender like there is a private channel that you might want to use, because the sender will not have that private channel uh, in his graph. So if the receiver has a private channel, that he might say like, hey, I have a private channel, like add this to your graph and like see if you can find some extra path or not. So it's up to the receiver to disclose his private channels or not, and that goes for everybody.
Okay.
Yeah. So the way I've understood it from the previous chapters is that, and from this current chapter, is you have the HTLCs and then you have the onions, and essentially Alice sending to Dina must construct the entire onion. She must construct every single layer of the onion. So that would imply to me that Alice must know every single node in every single hop in that path. So Alice, it seems to me like Alice would need to know about the private channel in order to fully construct that onion. And then to further extrapolate on that, I don't believe Alice is constructing the HTLCs, but I believe she is providing instructions for how to create the HTLCs for every hop in the path.
Yeah, that sounds correct.
So does that actually, I just realized, does that mean if you want to receive payment, but your node is not public, then that QR code also encodes, information about the private channel that you have? You need to give the payer, enough information to build the whole channel, to build the whole onion.
Yeah, they do. Like the invoice includes the private information. It's optional, I guess. Like if you want to like say like, hey, I have this private channel, like you can try sending me fund through this channel also. But if you don't want, like if you have public channel, then you can opt out for it also. So that's the sender like gets that information when he receives that invoice.
Okay. Thanks.
Yeah, but it's a good question. Like, is it even possible, like, to have this kind of like overall macro statistics about this like very frequently changing network? I saw some paper like trying to like do this for Bitcoin peer-to-peer network itself, like to try out some different parameters and see how the graph itself looks like. It was quite hard, like for Bitcoin itself, and Bitcoin is quite static than Lightning. Lightning is changing all the time, so it might be like orders of magnitude much more harder than that.
Well, also, it seems like the design also of Lightning is to sort of make that difficult. It's sort of a feature that they don't want you to see the topology or understand too much of the whole picture, just for privacy.
Yeah, the information itself is restricted on the like network graph, so not much information the node can gather, but it only gathers enough so that it can construct those onions. And yeah, and that's why the routing and this pathfinding thing is quite hard in Lightning, because enough information is about the domain or the terrain where the pathfinding algorithm needs to solve is available, and that's by design. So that's kind of like a hard thing to solve.
I wonder if it always has to be source routed. Like, I haven't heard of anything, but I wonder if there's any way that it could be hop by hop routed also, like.
Yeah, this proposal by Rene Picard is like this JIT routing, just in time routing, that kind
Mhm.
of like similar to our conventional routing. So the each at each hop, the hop decides what's the best way to route this thing, kind of something
Mhm.
like that. And instead of like failing the onion if there is not enough liquidity, so the hop will like rebalance the channel and then send it over there. And for that it will try to take some fees or something like that. It's called JIT routing, and it's like
Okay.
a parallel proposal to atomic multipath and like um, Tenderlion routing, something. The Tenderlion is the concept of like having some kind of like node hierarchy space, like master nodes, then like nodes of
Mm.
below that, then nodes below that, some kind of like IP address kind of like hierarchy, and that will
Right.
like help to like route like payments from places to places.
Which
And
is sort of
JIT
how the
routing is like, yeah.
well, as I say, that's sort of how the internet works now. It is a little bit hierarchical. Like you go to your ISP, and your ISP goes to their ISP, and their ISP goes to their. But it's sort of a bit of a
Yeah,
hierarchy
yeah.
of routing tables. Um, but anyway, what you were saying, there was another one besides these. You said there was the JIT and there was the source routing.
Source
What was that
routing is
other
what
one?
is used right now. So there is JET, that there
Right.
is atomic multipath. So AMP,
Oh,
atomic
multipath. Right.
multipath is the concept of like breaking down one payment into multiple chunks and like have it pass through parallel paths of like lower liquidities. And that's the atomic multipath. And Tenderloin is like having these like hierarchical address spaces. And JIT
Mm.
routing is like the it's like the hop is like deciding on its own in what's the best way to route this particular onion. But in that case, I think it will not even be an onion, it will be something else. I'm not sure, I haven't looked into
Mm.
details, but these are the proposal I have heard of.
That's interesting.
Yeah, because for each layer of the onion to be able to make a decision as to how to best do something, it means that it must possess some sort of information about where the payment is trying to go to. So that must be, maybe it's like,
No, it's like I just saw one presentation by Rene on this, and what how the way he explained is like, say Alice wants to pay to Dina, and it payment goes to Bob and Carol. Okay, so Alice pays to Bob, and Bob gets the onion, and Bob says like the instruction is like make a HTLC to Carol. Now Bob goes and sees his channel, and he doesn't have enough like outbound liquidity to make that HTLC. So in normal cases, what Bob will do is like Bob will send back this failure message to Alice is like, nah, payment can't go. But in this case, Bob will say like, I don't have enough liquidity with Carol, but I can rebalance my Carol's channel, and that will create enough liquidity. So then I can pass on this onion to Carol, and then the HTLCs can go on. And for that rebalancing, the Bob will take certain kind of fee, some kind of fee. I'm not exactly sure exactly how Alice will give the fee to Bob, but Bob will have some way to get the fee to do this rebalancing, or there will not be any fee, maybe. I'm not sure, but this concept is this, like if the payment channel doesn't have enough liquidity, then the send like the hop can like rebalance that channel and try to send that payment again instead of failing it.
I see. So
Does that make sense?
yeah, yeah, totally. I thought it was trying to find a different path, but it's not. It still tries to send the
No,
Carol payment.
it's basically rebalancing. As far as I know, it's just rebalancing. It's not trying to like create a new onion and do it in another path, because it doesn't know where it's going, right? So it cannot create a path for it. It just know like where it needs to send next. So if the next step doesn't have enough liquidity, he will create the liquidity and do the step.
Yeah.
I guess it might be an interesting thing here too in the Lightning is just the fact that you can potentially have multiple routing protocols, right? Like if your node, I mean, if these other proposals get implemented, you could have nodes negotiate that on terms of which routing protocols they support.
Yeah,
It doesn't have.
totally, and I think that's how they're gonna do it. They'll probably have like lots of parallel like routing implementation, and they will try it out in real time, like which one is
Yeah.
working best in what kind of scenarios. They can also like combine different proposals into new proposal, and those kind of things are also people cooking up. So yeah, and there is no restriction here. It's not consensus critical, right? So it's just like
Yeah.
a plugin. So your L&D node can have an extra plugin that will do this kind of routing.
Yeah. That's actually really powerful in terms of quickly iterating on finding a better solution. Ideally, I mean, it still probably takes a long time for it to be a new protocol to be widely deployed enough to be useful, but it's at least something you don't have to wait for a consensus on. I think that's a really key.
So that's the good part
thing.
about many things in Lightning. Lightning is not a consensus protocol, right? So after, like once you agree with the bolts, like the basic standards of like doing this HTLC thing, then like everything else is can be like played around in different terms. That's a good part, and that's why I feel like Lightning is also moving very very fast. Like lots of development of happening.
Yeah. Yeah, it's okay for Bitcoin to move slow if Lightning's moving fast on top of the slow stuff. Yeah. Although Bitcoin's been moving pretty fast lately.
To me, it seems like everything is moving very, very fast everywhere. I can't even keep track of like what's happening where.
Yeah, I mean, because again, all this is it going to affect the routing when the whole taproot stuff happens? I think it will, because at least the information hop to hop will change with the point time lock stuff, so that'll have some impact at least.
Yeah, I see like Taproot will take a long time to get adopted in the Lightning phase. The Bitcoin Optic is like releasing this doc series where like they're addressing like what kind of like adoption or what kind of like preparation different application needs to have, and they have a very big Lightning section over there. So lots of things can be done on Taproot for Lightning, but it's gonna take a few time to like roll out all the stuffs. But yeah, it's pretty exciting. It opens up like lots of new ways of doing stuffs.
Nice. I'll go check that Optech one. That sounds interesting. So, any other topics from this chapter? This ChaCha thing was interesting. I had heard that term before, but I hadn't actually understood what it meant or what it was. But I guess it's a scheme for deterministically generating random data. Did I understand? Anybody else?
What was that term you said?
It's a ChaCha 20. I guess it's an algorithm, a crypto algorithm for generating random data. It's used, I guess, it's ChaCha 20 actually.
I was like, I thought he was saying ChaCha, but I could not. Oh, I see.
Yeah, it's ChaCha 20. Yeah, I'd heard that term before.
It's basically an HMAC algorithm as far as I know. Like there is some RFC that describes this algorithm, and Bitcoin Core also uses it in some places. It's called ChaCha 20. It's a funny name, yeah. So basically what it does is like kind of like hash. It's similar like in hashing function. Like with hash function, you can like generate this pseudo random like strings of numbers, right? With ChaCha 20, you can do also the same thing. It's mostly used in like HMAC kind of construction for message authentication, like hashed message authentication. So you know like your message is the correct message that it was supposed to be, kind of like a checksum. So yeah, it's used in a lot of places, in different places. It's kind of I have seen it like used in places of like pure hash functions also. Like instead of having a SHA-256, they had like ChaCha 20. So it kind of works in the same way, but it's basically designed to be like this HMAC thing for authentications and all these kind of like proofs and nice stuffs.
Okay, so message authentication being you're not just proving that the message. I guess it's a stronger guarantee that the message wasn't altered, right?
There's some way of putting that, and like with checksum is like very like crude way of doing the same thing, but it's a stronger guarantee in that sense.
Yeah,
it also like has some like can be linked with the public key that is used to derive that function also. It probably takes in like a random bit string as a entropy in order to like generate these like hashes, but it does it deterministically. So if you have the same random string and the same message, it will create the same hash. I'm not sure. Like I'm guessing. I just looked at it like years ago in some Bitcoin review club, and SIPA was like the guy who is mostly does this crypto magic coding stuffs for Bitcoin. So all the ACCP libraries and the crypto libraries are done for SIPA. So he hosted a very nice review club meeting, and I learned a lot, but I forgot. So this is the only part I remember.
Yeah, I think that's a good. I mean, like, it's enough to understand what they're used for. Yeah, I just, that's where I usually try to go, is just what the basic use case is without understanding all of the necessarily the crypto math details, because it's just good to know sort of the context of how these get used in terms of, you know, where you might expect them to be used, or what their kind of general high level purpose are. I always find that at least is good to know, is interesting to understand.
Yep, makes sense.
And then he also uses another one of these crypto primitives, is this diffie-hellman key exchange, right? I forget the acronym. Is it? I think that's at the beginning. I'm just checking here.
So that thing is not like a like it's a very generic algorithm. Like it goes back to this nice story of 1970s, like when this Whitefield Diffie and Mark Hellman, I guess, they invented public key cryptography. So it's basically the start of public key cryptography. So that's the algorithm. Like if you have two public keys, then these two party can like create a shared secret without knowing each other's private keys. So then they can like encrypt stuffs to this shared secret, and each other they can like both decrypt it correspondingly. So that's when all this like public key thing got started in cryptography. So that's the Diffie-Hellman algorithm of like how to create this shared secret. They also had this like nice math where they give this like on like warning of like this will tear you up. Yeah.
Yeah, I think what I found interesting about this whole Diffie-Hellman stuff, and it's in this case, I guess, elliptical curve, ECDH, but is that when you have two elliptical curve public-private keys, you're not actually encrypting stuff with those public-private keys. You're just using them to create this shared secret, and that's what you actually use for encrypting your messages. So it's sort of a, I don't know. When I first came to understand this, I thought it was a little non-intuitive that you have a public and private key, but those public and private keys are not what you actually encrypt your data with. You're using those to generate this shared secret, which is actually what you're using to encrypt your data with. I just thought that was fascinating, and it seems to come up everywhere. You know, it comes up again here in this onion routing. So yeah, just more of an interesting crypto high-level concept.
This is part of the chapter where I start to get a little bit lost. I mean, I'm familiar with Diffie-Hellman and the elliptic curve generator point kind of stuff, but so I'm looking at the graph now that shows it like, you know, using the SS, the shared secret, and then piping that into the HMAC key generation function, and then that gets piped into RHO, MU, UM, and PAD. So is the purpose of using the shared secret as the HMAC key generation function, is that so that other nodes along the hop don't identify you by your like private key, your node's private key or your public key?
That's a good question.
I guess so. This is the part like I haven't got into more detail, but one question I have is like when you are creating a shared secret, like to decrypt and encrypt any kind of data. Like say Alice and Bob like came together and they created a shared secret, and then they use this shared secret to encrypt a certain chunk of data. Then Alice can send this data to Bob, and Bob can read it out because they have the shared secret. But the question is like, when the same data goes and reaches to Charlie, how does Charlie reads it? Because Charlie doesn't know where the or Alice and Charlie never created a shared secret, right? So I have to like this is the part that I haven't like looked into detail, because this is I have to take some time and like see all the details to understand properly. So I have kept it for later. But this is an interesting question. I think this is like somehow handled in the onion creation, because Charlie or all the hops in between should know how to decrypt their data. Uh, or like for other hops, is it like that Alice is like the sender for other hops other than the immediate node? It's just encrypting into their public keys itself, because
Yes, I
if
think
it
that's what I was gonna say. Yeah, that's what I read. She encrypts using the public key of all the hops, basically.
so you just do this shared secret magic with your immediate peer, because you don't want him to know where the onion is coming from, right? I guess so. Because in other cases, like if you in other cases, obviously the sender is not going to create shared secret with everybody in the hop, right? So he is going to encrypt the rest of the stuffs to the public keys of other hops. But this uh, shared secret thing, I think it only gets created for Alice and Bob. I'm not sure, I have to check.
Okay, so we're about
Well, and I think there's
45 minutes in here, so I
levels.
think I'm going to go ahead and stop the recording here.
Sounds good.
See everybody next week.